Hello everyone. Today we're going to talk about section 15.2, double integral on general region. Yesterday we talked about double integral on the rectangle. Okay. Today we're going to talk about general region. So that means the region is not rectangle. Okay, most of the time it's not. Okay, this section, if you look at your textbook, it sounds like it's short, but we're going to spend 2 days to talk about it. I'll try to talk about more examples. Okay, so let's get it started. Okay. Okay, Math 1D. This is a lecture 14. Okay, so this is section 15.2. We talk about double integral. Double integrals over general region. Okay, so we're going to look at part 1. Okay, the first part of this section talk about under what condition the integral is integrable. Okay, so that part I'll let you read the book. Okay, so first of all they talk about the region is bounded by a rectangle, and then so within the rectangle you define another function. So the function capital F is equal to the given little f on D, and outside D within the rectangle, and the function capital F equal to 0. So that part I'll let you read the book, and then talk about it under what conditions are integrable. And then I'm going to directly go to talk about how do we do the double integral. We're going to talk about several cases. So the first case is, we say if f x, y is continuous on type 1 region D. Okay, now what is the type 1 region D? Type 1 region D is this. So D is equal to, so here is x1, x2, and xy, such that x is between two constants, between a and b, and y is between two functions g1x less than equal to y less than equal to g2x. Well, of course, g1, g2 could be constant, or one of them is a constant, okay? Or both are not constant functions. So this is called the type 1 function. Then we have the double integral is like this. So we say integral on D of f x y dA is equal to, so here we say the iterated integral a to b, and then we say g1x to g2x, and then say here's the f xy dy dx. So we have that. Okay, now let's look at one example. Okay. Example 1. Okay, we say find the volume of the solid enclosed by the, okay, we say paraboloid, paraboloid z equal to z equal to x squared plus y squared plus 1, and the planes, we say x equal to 0. X equal to 0 is a vertical plane. Okay, y equal to 0 is a vertical plane, and z equal to 0 is a horizontal plane, and we have x plus y equal to 2. So this again is a vertical plane. Okay. Now, if you want to find a volume, okay, so let's look at the what the solid looks like. Okay, so here we say solution. Okay, now we can draw the picture, okay, the way we want. You can imagine and then think about what direction is good, and then so here we say suppose this is a z-axis, and then this is x-axis. Okay, this is the x, yeah, this is the z. And then, well, suppose this is the y-axis, okay? But I'm going to use dash lines. Okay, so this is a y-axis. Now you think about this paraboloid. When x equal to 0, y equal to 0, z is equal to 1. Z is equal to 1. Let's see. So here, suppose this is a 1. Okay, suppose this is a 0, 0, 1. And then, let's see. X plus y equal to 2. So x plus y equal to 2 is like this line. So this is a, okay, equal to. Now, when x equal to 2, yeah, I think maybe I should move the y a little bit, one little bit higher. Whoops. Yeah, I think little bit higher, say move it here. How about that? And then now you see when x equal to 2, 2, 0, 0, then z must equal to 5. Okay, so z equal to 5. I'm gonna put it like this. So here, suppose this one. Okay, yeah, I think it. Okay, I think so this point, here we said this point is 0, 2, 0. And then, how about this is a 5? How about we say this part, z equal to 5. Okay, and then we have, let me see, this one. Okay, now you think about it well, those 3 points are on the paraboloid. Now you think about it, if x equal to 0, x equal to 0, z equal to y squared plus 1 is a parabola. So here is like this, the parabola. So this part we should be able to see. And then if y equal to 0, z equal to x squared plus 1 is a parabola. Okay? Yeah, I think something like that. And then now you think about the vertical plane, x plus y equal to 2. This vertical plane caught the paraboloid, and then we should have this paraboloid. Okay, something like this. Okay, so here we say, well, you see this part on the top, this is a z equal to x squared plus y squared plus 1. That's the top. And then okay, the bottom one is z equal to 0. The bottom one is z equal to 0. And then this front one is y equal to 0. Front one is y equal to 0. And then we say, well, this side, say here we say this part, this vertical plane is x equal to 0. X equal to 0. So this form a solid, okay? Form a solid. And then if you look at the planar region, planar region, of course, is just like this. So this is the x, this is the y, and then this is the x plus y equal to 2. So this is a D, okay? This is a D. This is the planar region. Okay, well, the D is at the bottom, that's D. Okay, so that's like this. Now, before we set up the integration, it is always good to write what is the D equal to. So D is equal to, say, here's the x, y, and then, well, we say this is a 2, this is 0. So we say x is from 0 to 2. And then you give a x value, say here is the x value, y change from here 0 to here. So then we say y change from 0 to 2 minus x. That's a function, because this implies y equal to 2 minus x. Okay, so it's like this. Then we say, when we set up an integration, we say the volume is equal to 0 to 2, and then 0 to 2 minus x of z x squared plus y squared plus 1, and then dy dx. Okay, so now we said this is easy to integrate. Okay, first of all, you integrate with respect to y, treat x as a constant. So that means you're going to have x squared y plus 1/3 y to the third plus y. And then you substitute, okay, remember y equal to, well, you can put y equal to 2 minus x and y equal to 0, or you don't need to put y, just put it 0 to x 2 minus x. So when you substitute in, so we're going to have this, okay, so here when you plug in x times 2 is 2x squared times 2x squared minus x to the third, and then plus 1/3 2 minus x parenthesis to the third plus 2 minus x, and then we say this is the dx. Well, when you plug in 0, everything is 0. Okay, and then so this we're going to have this 2/3 x to the third minus 1/4 x to the fourth. Well, this third term you don't have to multiply out because dx equal to negative d2 minus x. If you do substitution, net u equal to 2 minus x. So you're going to have this is a negative 1/3, 1/4, and then 2 minus x to the fourth. Well, you think about it, when you calculate derivative, this 4 come down, cancel this 4, and then 2 minus x squared, 2 minus x to the third power times the derivative 2 minus x, which is a -1, cancel this -1 in front, okay? And then here's a plus 2x minus half x squared. And then this whole thing, you're going to plug it into 0, okay? So now you're going to have, when you plug in 2, okay, 2 to the third is 8 to 16/3 minus 16/4 minus 1/12. Okay, when you plug in 2, that's a 0. Minus, okay, the 0 plug in, that's just equal to minus negative positive times 16. And then when you plug in 2 is a 4. Okay. Yeah. So this is a 4 minus half times 4 is a 2. So we have this. Now 16/3 minus 14/3 equal to 16/12. And then you have a 16/12, that's equal to 16/6. So that's equal to 8/3. And then plus 2. Okay, so that's equal to 4 and 2/3. Okay, so this is a, yeah, I think that this is review your math 1B and do some integration. Okay, now notice this one. What we said is we said is type 1 region. But next, we're going to see type 2 region. You can see this can also be treated as a type 2 region. Okay, so we say second part. Okay, we say if f is continuous on type 2 region, type 2 region D. Now here we say D is equal to, so we say X, Y, and then type 2 region is like a Y is between C and a D. And then X between H1Y to H2Y. So X is a function of Y. Then we say this integral, double integral D, f x y dA is equal to, we have from C to D, and h1y to h2y, and then f x y dx dy. Okay, so you see, if in application the last integral always between constants, the upper limit and lower limit. Okay, so let's look at another example. We can do the same problem, treat as a type 2 region. Sometimes type 1, type 2 region, the same region we can treat it either way. But sometimes we have to we have no choice. We're going to see some other example, but here I'm going to put a different example. I'll let you do the previous example. If you treat it as a type 2 region, what you need to do. So here we say example 2. Okay, again we say find the volume of the solid bounded by the cylinder. By the cylinder, we say y squared plus z squared equal to 4. Or we say it's equal to 2 squared. And the planes. And in the planes, x equal to 2y. X equal to 0. Z equal to 0. In the first octant. Okay, so like this. Now again, if we draw the graph, yeah, I think I say this is double integral, and then a lot of times involve geometry. If you can draw the graph, that's really help. Okay, so here let's see. We have, if we draw z-axis this way, and then we said this is the x-axis. X-axis. Now y-axis is this, so I'm going to, yeah, I think I'm going to put a dash line, because before you draw the graph, you need to be able to imagine what's the geometric figure looks like. Okay. Okay, so here we say this is the y-axis. Now, if you think about it, y squared plus z squared equal to 2 squared. So on the yz plane, okay, yeah, I think this is a z. On the yz plane, it is a circle. Center of origin, radius is equal to 2. Okay, so here, well, we want to draw, we wanted the geometric figure on the first octant. So we draw a quarter of a circle. So suppose this is a quarter circle. So this is a, this is a y squared plus z squared equal to 2 squared. Now you think about it, this is because the x is not there, so x can be anything. So the surface should parallel to x-axis. But we need to know, say here, when the plane x equal to 2y is a vertical plane. So when y equal to 0, x equal to 0. When y equal to 2, x equal to 4. So how about it, we say something like this point. Okay, suppose this point is x equal to 4. And then y equal to 2, and then we have this this straight line. Okay. Now you think about it. You have a vertical plane to cut the surface of a cylinder. So you are going to have what? Well, this is a. We should be able to see this part. Okay, and then when you cut that, you're going to have a. Yeah, you're gonna have something like this. Okay. Now, if you okay, so if you want to see this is like this, so here, well, of course, if I draw some, if I shade some surface is like this, so this is the cylinder, part of the cylinder. Okay, this is a part of a cylinder, and then of course this is a vertical plane, so if I want to shade this one, I use vertical lines. So something like that. Okay, so now you see this part we say is a y squared plus z squared equal to 2 squared. And this is 0, 2, 0. And then that's 0, 0, 2. Right? This is the origin. Okay, I think here we say this point z equal to 0. That's this point. Okay, and then we say this vertical plane is x equal to 2y. Is x equal to 2y. Now, if you look at the planar region, okay, the planar region, so this is the x-axis, y-axis. Yeah, I think of the x. Sorry, this is the y-axis. So this is the y-axis. Okay, so this is a y. This is a x. Now, so we have, okay, and then here this is a x equal to 2y. Okay, and then this part is say, well, here is a 2. And now we say, well, okay, so this is a D. And then, of course, this is a x equal to 0. So when you look at this, we say the region D, we can write it like, say here, D is x, y, and then we say y change from 0 to 2. Okay, then x change from 0 to 2y. X change from 0 to 2y. Okay, and then now we say the volume V is equal to, say, 0 to 2, and then 0 to 2y. And now we have, say, here, square root of 4 minus y squared dx dy. Dx dy. And now you see here, this is equal to 0 to 2. Now, the first integration with respect to x, but the function has no x. So it's like a constant. So you move out 4 minus y squared. Okay, 4 minus y squared. Well, because here this means z is equal to square root of 4 minus y squared. Well, when we take a square root, we need to think about positive, negative, but here we say in the first octant, so z must be positive. And then here is, so if you want, you put x, substitute 2y, and then 0. So it's like this, dy. So basically it's just a 2y. Okay. Then if it's a 2y, so we can do a substitution. Let me do one more step, 0 to 2, and then 4 minus y squared to 1/2. And then here is a 2y dy. Now 2y dy is a dy squared. And then, so here we can put it this as 0 to 2, and then 4 minus y squared to 1/2. Now, let's see, d 4 minus y squared, okay, because of d 4 minus y squared equal to the derivative of 4 minus y squared equal to negative 2y times dy, and then negative cancel the negative 1, okay. So yeah, I use the implicit substitution, let u equal to 4 minus y squared. So you're going to have, say here, negative u to the half du. So that's equal to 2/3 u, which is 4 minus y squared, to 3/2. And then plug into 0. Because when you calculate derivative, 3/2 cancel 2/3, so 3/2 minus 1 is 1/2. The derivative inside, that's just just like a d, 4 minus y squared. And then when you plug in 2, that's 0, minus negative positive 2/3. And then 0 plug in, so that's just equal to 4 to 3/2. 4 to 3/2, so that's 4 is 2 squared, cancel the 2, so 2 to the 3rd. Okay, so that's 16/3. So basically this is equal to 5 and 1/3. Okay, so that's like this. Now, if this one, maybe some people think that, well, can we use a type 1 region? Say if you think about a type 1 region, let's try this. Say here, if you look at D, of course D can be written as x, y, and then, well, we say x change from 0 to 4, right? Now y change from, okay, so if you look at it, this is a 4. X change from 0 to 4. Now y, if you give an x, y is changing from here to here. So if you solve the equation for y, y equal to half x, okay, to 2. So half x to 2. Okay, so if I treat as type, so this is a type 1 region. Okay, it is true a region can be type 1 and it can be type 2. Depends on how you describe it. Okay, so if I have that, then let's see, is that, how do we integrate it? So we say the volume is from 0 to 4. And then from half x to 2. Now z, okay, because you still have this root 4 minus y squared dy, okay, dx, okay. Now you see, how do we integrate this one? Okay, now you see, this is this part, okay, this part is much harder to integrate than this part here, because the first integral, this one, root 4 minus y squared, is a constant with respect to x, so this can move out, and then you have a 1 dx, the antiderivative is x, and then after you have this, you have 2y. 2y you can put it into dy squared. So this is much harder to integrate. I'm not saying it's impossible. You can try this. I'm not going to finish this. So you can see sometimes even though the region can be written as type 1, type 2, and then sometimes one integral is much easier than other integral. So when you think about which one to use, and then you need to try. Well, if you try the first example, okay, let's look at the first example. First example, because there is no square root, and then if you look at it, they say here, the first example, I think the difficulty level for both are pretty much the same. Okay, let me see, because if you look at it here, you have both x squared plus y squared. So that's like with respect to x and y is like a symmetric. So if you think about, say here, let's see, we say for, how about the little bit extra, I'm going to say, whoops. Okay, let's see. If you look at it, we say for example 1. Okay, if you describe the region as type 2 region, okay, type 2 region, so that means you describe y first. Okay, now y change from 0 to 2, and x change from 2 minus y. So here we have, say here, y change from 0 to 2, and x change from 0 to 2 minus y, yeah, 2 minus y. And then, now this is a type 2 region. Okay, now you see the volume is equal to, we say here is 0 to 2, and then we have a 0 to 2 minus y. And the function is x squared plus y squared plus 1. And then we have a dx dy. Now you see the integrand. The integrand function, x squared plus y squared plus 1. So it's a symmetry about the x and y. So now if you set up this one, if you integrate it, it's almost exactly the same. Okay, so you can why don't you continue integrate this, finish this? So you're going to get it. The difficulty level is the same, so you can integrate. This is a okay. Okay, I'm going to put it here, the evaluation is the same as in example 1. Well, why don't you try to complete that? So you can see from example 1, we can use either type 1 region or type 2 region, the integration, almost the same. But example 2 is different. If you change to type 1 region, the integration is much harder. Okay, you can try. Okay, so that's the integration. If you remember this, probably you're going to use the trig substitution. And when you use the trig substitution, the angle, you have a half x to 2. That's caused difficult. Okay, you can try some few steps and then see how to integrate. So it's much harder than the way we did for example 2. Okay, so we're going to spend more time on this section. So first of all, we talk about it, the type 1 region, type 2 region, and then maybe next tomorrow, let me see, on Monday, I'm going to maybe talk about an example. So when you look at it, the region, maybe you have both. Okay, maybe you need to break up into two, the planar region, or it's more obvious if one is easier than the other one. So we need to think about how to choose. Here, example 2, you already see one is easier than other one. And then sometimes we're going to see there's only one way to describe the region. So this double integral, later on we talk about triple integral, basically describe the region is very important. So I strongly recommend that every time you do integration, first of all describe the region. Okay, describe a region, and then you set up the integration. Okay, so please read this section. Okay, and then stop. Okay, please read this section and then start to do the homework problem. Okay, yeah, during the weekend, and then try to do as many problems as possible, and then on Monday I'll talk about more examples. Okay, so if you have time, and then yeah, I think as I said, section 15.1, the only last topic I didn't talk about is the average value. That's just a formula, so that's the very last page of that section. Talk about average value. The first review the average value of a function of one variable, and then talk about the average value of a function of two variables. If you have a question, please let me know. Okay, I'll talk to you on Monday. Have a nice weekend. Okay, bye bye.